morning. In this lecture, continuing with our discussion on physical design automation techniques, we will be looking at the placement problem. Now, I had mentioned in my earlier lecture that the process of floor planning and placement are somewhat similar in concept, and in many cases they are done together. So, when you are doing floor planning, you are merely trying to find out a relative ordering of the blocks. But while in placement, in addition to the ordering, you also try to find out the actual amount of space that you must leave in between for the routing or interconnection of the nets, you mean say. So, the interconnecting nets, some space has to be left between the modules so as to interconnect them. So, our topic of discussion today is placement. Now, placement clearly is a very important step in the design cycle of a VLSI chip. The reason is very clear. If you have a poor placement, then typically the length of the nets would be pretty long, and moreover there will be congestion in the routing regions. Okay. So, it will require larger area in general. This larger area will primarily arise out of increased area required for interconnection, and since some of the nets may become longer, they may be critical nets also. So, in general the performance will degrade. Now, essentially placement means you have a set of modules, you want to arrange them on a layout surface. In this sense, this is very similar to floor planning, but I had mentioned that in case of a floor planning you are trying to find out a tentative arrangement, but here it is more like an exact arrangement or finding out the exact location of the modules. Now, at the level of placement, unlike floor planning, we assume that all the modules have already been finalized in terms of their shapes and in terms of their terminal locations. Well, in floor planning some of the modules may also be flexible, but when we are dealing at the level of placement, they are all fixed. And moreover, some of the modules may already have some pre-assigned positions in the chip. For example, the input output pads. Well, if your chip is of a rectangular shape, then the position of these IO pads may already be fixed, because IO pads also involve some circuitry. So, the circuitry can be treated as modules, and the position of those modules in the chip may be fixed. So, some of the modules may be fixed in terms of location, and some other modules you will have to place them suitably. Okay. So, I am just showing you an example in order to illustrate what is the difference between a good placement and a bad placement. Just have a look at this diagram. The top diagram shows some of the blocks which are called A, B, C, D, E, F, G, H, etc., with some points showing the net connection numbers, like 1, 1 and 1, they have to be connected, and so on. Now, you see the two extreme alternatives. This of course denotes a good placement, where you see that the interconnection nets are very regular and local in nature, but while in a placement like this you see that you require long interconnecting lines. Okay. So, the lines will become long in general, there will be some crisscrossing of the lines. Well, so one thing you note, this is typically the output of a placement algorithm, these two diagrams I am showing here. Now, here you see that I am still not finding out or determining the exact path through which these nets will have to be routed. For instance, just you think of a line which goes from here to here, for example, but in practice the routing line may be like this, but at the level of placement we are approximating them as a straight line connecting these 2 points. Well, we will see that there are ways of estimating the length of the interconnecting line, but this will give you a fair idea regarding how difficult the routing will be in the next step. Okay. So, as I had mentioned, the inputs to the placement problem will be a set of modules with of course well defined shapes, they are fixed, and the location of the pins are also fixed, and in addition a netlist which will tell you how these modules have to be interconnected. Requirement is obvious, find the location of each module so that no two modules overlap, because overlapping modules are not acceptable for obvious reasons. So, you will have to find out disjoint locations for them on the floor of the silicon. And secondly, you will have to keep aside sufficient space between the modules to take care of routing in the next step. So, the placement has to be routable. So, in terms of the objective, of course, you will have to minimize the layout area. Now, layout area will consist of two things. One of course will be the area of the basic modules plus the area occupied by the interconnections. Yes.
The area of the module is fixed.
Area of the module is fixed. Yes.
So, like when you say minimize the layout.
Minimize means the area of the module is fixed, you cannot do anything about it. But one thing, the way you place it, you may find that some of the space in the floor area is they are lying unutilized. So, it is just not the sum total of the module areas. Of course, reducing length of critical nets and completion of routing are some idea. Well, one thing I may also mention here, that well, in terms of the placement problem, what we are trying, as I had mentioned, that we are trying to find out the location of the blocks and also the space between them which will be sufficient for doing the routing. Well, some of the tools, what they do, they before the placement step starts, they expand the size of the basic modules. For example, this module will become this big, this module will become this big, this module will become this big. The reason is that the way they expand the modules is that the additional area you are keeping aside in the boundary of these modules, this additional space, these are actually the space you are keeping for routing. So, once you do this, then the placement and the floor planning problem becomes very similar. So, there are some tools where floor planning and placement are done together, there some technique like this is also adapted. Okay, fine. Now, in fact, in practice you can carry out placement at several different levels. Suppose that your objective is to design a large system, say a large system, it may be something like a computer system or a dedicated application, where there will be several printed circuit boards which will be going into a cabinet or a chassis, and inside the PCBs there will be ICs, and inside the ICs of course there will be blocks or modules. So, at the highest level you can talk about system level placement. System level placement means I have the system, I have the cabinet. Now, inside the cabinet I have to place the printed circuit boards together. Now, the way I would be putting the PCBs together is that of course, the total area occupied inside is minimized, and secondly the heat dissipation should be uniformly distributed. So, there should not be any concentration of heating in one portion inside the cabinet, so that there will be some circuit malfunction due to increased temperature. So, heat dissipation should also be controlled in a suitable way, that how we will be spacing out PCBs, which PCBs will consume more power, they will have to be spaced apart or something like that. So, at the level of system we are treating with PCBs as the basic modules and how to put them together, it is a very high level thing. But once we go inside the PCBs, we have what is called board level placement. So, here the PCBs are given and we are given the task of assigning the chips or the components inside that PCB. Now, since my overall design of the system is fixed, so I have a choice that which chips I need to put in here. Well, I am not really talking about a system like a PC where the cards are very well defined and the functionality of the cards are known. But rather I am talking about a large dedicated system where what you put on the card is up to you. Okay. So, here the chips have to be placed on a PCB. The requirements in this case are, see, once you have completed a system level placement at the top level, or means you have done a system level design, the size of the boards are fixed. So, the total area is fixed and the chips and the other components, they are all typically of rectangular shapes. So, there is no irregular shape involved. An objective is minimize the number of routing layers, because you know today the PCBs are all multi-layer PCBs, and interconnection between the chip pins, they are carried out not on one or two layers, but several layers. The layers are all sandwiched together one after the other with some through holes which connect one layer with the other. Okay. So, if you have multi-layer PCBs, then the interconnection area becomes very less. So, you will see in today's PCB the chips are so close together. Okay. So, of course, more the number of routing layers, more will be the cost of the PCB and less will be the reliability. So, one objective is to have a design which will minimize the number of routing layers. This will bring down the cost as well as increase the reliability. Of course, performance requirements is one issue. We will have to look at the critical paths and other things. This is what we call board level placement. Then finally, we come inside the chips. This is the chip level placement. So, now inside the chip level placement, we have the complete flexibility. We have the floor of the silicon, we can place the blocks and modules inside this. So, all the conventional floor planning and now the placement tools and algorithms we will be talking about, they may be applied to this case. Pin assignment is also an option if you are going for full custom design. Okay. Now, in case of chip level also, depending on the fabrication technology, the number of routing layers are limited. Well, in PCBs, if you need more number of routing layers, you can have, you can sandwich more number of layers. But in an IC, depending on the fabrication technology, you can have, well, anything from 2 to 4 layers which are typically on metal, which are available to you for interconnection. So, this is a given thing, you can say some kind of a constraint which is available to you. And since the number of layers are limited for routing, so if your placement is bad, you may have a design where you cannot complete the routing. You will say somewhere there is a conflict, you cannot find a route for the last few nets. But the problem is that the placement is unroutable. This can be found out only much later while you are doing the routing. So, if you find out during routing that the placement is unroutable, you will again have to go back and change the placement and do it again. So, this is a costly delay in the overall design cycle, but you will have to live with this. So, a good placement is very important. If the placement is good, you may not have to iterate in this way. Yes.
Sir, in board level, are there any constraints on the number of layers?
Board level, well, typically the way they are manufactured, if you say that I want 8 layers, they will provide you 8 layers. But typically the layers are kept between 4 and 6 due to concerns of reliability, but the number of layers can be increased if you really want.
So, board level placement deals with placement of chips?
Chips and the other components.
Chip level placement is placement of?
Placement of the circuit modules inside a chip. Okay. Of course, here one criteria is minimization of area, that is important. Okay, fine. So, now let us try to formulate the problem mathematically. First, we introduce some notations. Let B1 through Bn denote the modules or blocks which are to be placed. There are n such blocks, and each block, say block number I, Bi, will be having a width of Wi and a height of Hi. So, Wi, Hi are the width and height of the blocks, which in the placement problem is also given and fixed, and N is the set of net lists. Well, N1 into Nm, I am assuming there are m such nets. Each net means a set of pins. This will constitute a net. For example, the problem of connecting these 4 pins will constitute my net number I. There are m such nets. Similarly, in the placement, when you place the blocks, you will be having some vacant places in between. These vacant places you call queues, Q1, Q2, etc. So, these queues are the rectangular empty spaces which are kept aside for routing, and Li denote the estimated total length of net Ni, total length of the wire you need to route this Ni. This is the estimated length, because at this level you are not doing the exact routing, you are only trying to find out a good estimate. This Li denote the length, right? Yes.
So this length is calculated on straight line?
Yes, I will come to that. There are a number of ways of estimating this length. Well, some kind of a straight line, some kind of approximation to the reality. Okay, we will see that. Yes.
So the free space that you talked about, so it's a connected space. How can you?
It is a connected space, but you can partition it into several rectangles, because some of the space may be L-shaped, they may be cross junctions, that you can divide into a number of rectangles.
So if you have an L shape, you consider this to be a rectangle.
Now, what I am saying,
Rectangle or this?
yes, I am just coming.
Be an overlap.
Suppose you have a free space like this. This is a free space. There is one block out here, say this is B1. There is a block out here, B2. There is another block out here, B3. Say, now what you do? This is also free space. So you either divide it like this or divide it like this. It's up to you. Suppose I divide it like this. So this I call as Q1, this I call as Q2, this I call as Q3.
Because we have all these automated tools, how do we know how it will divide this?
See, this we shall come a little later when we go into the problem of global routing, because this concept is not really required in placement. This is just a notation we are introducing now, but exactly how these regions are defined, that we will see in detail later when we talk about global routing. Okay. Given the overall placement, how do you define these rectangular regions? The next subproblem is that for each net, which is the sequence of regions that need to be traversed. Okay, so this problem will be coming to later. Well, the placement problem is, well, the blocks B1, B2 through Bn are given. The placement problem says that you find rectangular regions R1, R2 to Rn such that a block can be placed into a region. Now, the size of the region may not exactly match with the size of a block, because you may not be able to fit exactly. Well, what you really require is that Ri should be greater than or equal to the size of Bi. This Ri can be bigger than Bi also, you can place it there. So, block Bi can be placed in region Ri. No two such rectangular regions will overlap, obviously. Placement is routable. So, the rectangular empty spaces which are available, they are sufficient for routing. Total bounding area of R and Q. R represents the place we are putting the modules, Q represents the space which are kept aside for interconnection. The total area is minimized. Now, in some cases where you are looking at the total area, you may want to minimize the total wire length sigma of Li, or in cases where you want to minimize the critical paths, max of Li may be minimized. The maximum length of a net you may choose to minimize. Well, it depends on your requirement. Either you choose to select choose to minimize the overall wire length, where the total wire length will be minimized, or you may choose to minimize the maximum of the wire lengths, so that the total length of the wires will remain within bounds. Well, the point to note is that the general problem to solve this kind of a situation, this has been shown to be NP complete. So, we cannot go for an optimal solution, and all the algorithms and techniques we will be discussing, they are heuristic or they are some kind of randomized in nature. Okay? Fine. But the first thing we discuss before we go into the algorithm is that, well, when we talk about placement, we are saying that we want to talk about minimizing the wire length, well, either the sum of the wire lengths or the maximum of the wire lengths. Now, at this level, at the level of placement, we are not exactly finding out the paths through which the wires will be laid out in terms of the individual nets. So, we will have to find out a very good estimate regarding the length of the nets. It means how much silicon area will be consumed for each individual net. So, these are the so called interconnection topologies, and these are very important in case of placement. You recall in floor planning, we had used some simple estimate like Manhattan distance to compute the cost of interconnection, but here we will be refining the concept, we will be having some estimate which is more accurate. So, let us see how we do this. Fine. So, in order to make the estimate, so means we do not know the actual wiring path, we want to make a good estimate. So, in order to make the estimate, we model the topology of the interconnection nets. This is important. Interconnection nets means, again I am telling you, it is just a sequence of pins on the surface of the blocks. This will constitute a net number, say I. You will have to connect them. So, you will have to model this topology somehow in the form of a graph typically, and with respect to the graph we will have to find out the cost. Okay. In that graph, vertices are the terminals you want to interconnect and edges are interconnection. Suppose this is one example of a graph. Edges are interconnections, vertices are the terminals. Okay. We will be looking at the different graph structures which have been proposed and how the estimate has been done, we will be seeing that. But first, before that, let us look at some basic things. Well, first is the estimation of well means, of course, we are modeling the interconnection topology with the objective of estimating wire length. Now, the speed and quality of estimation, how fast we can estimate this and how good we can estimate this, these things will indirectly depend or means will indirectly control the performance of the placement algorithm, because if we have a bad estimation, then the placement may not be very good. Well, if you have a good estimation which is also running very fast, then maybe the placement can be done very fast in a good way. Well, for estimating wire length, if it is a 2-terminal net, the problem is simple. If there are only 2 terminals to be interconnected, this is your net number I say, then you simply compute the Manhattan distance. Manhattan distance, you recall, this is the rectangular distance like this. So, if you have the xy coordinates of these 2 points, the Manhattan distance will be the difference of the x coordinates plus the difference of the y coordinates. So, the Manhattan distance of 2 points whose coordinates are x1, y1 and x2, y2 can be written as difference between x1 and x2 plus difference between y1 and y2. Well, Manhattan distance is used very widely in routing, because that is normally how we try to interconnect. We do not connect by diagonal lines, we connect by horizontal and vertical lines only. But the problem arises if the nets are multi-terminal in nature. If instead of 2 I have to connect 4 or 5 points in a net. So, in that case how to estimate the length? Okay. There are yes. We can take them in groups of 2, yes we can do that, but there are other simpler ways also. Well, so now let us see the different alternate ways in which people have talked about estimating length of multi-terminal nets. Well, first we will explain this, then we will just have a look at an example. Complete graph is a very simple way to look at the problem. Well, here essentially it is the same as what you are talking about. You take each pair of them, you connect them as a 2 terminal one. Complete graph says that if there is an n pin net, then you model the topology where every pair of pin is connected by an edge. It is a complete graph. Suppose if it is 4 nodes, you connect them like this. So, it is a complete graph. So, if there are n pins, the number of edges will be n choose 2 or n into n minus 1 by 2, right, in this graph. But you recall, well, in practice what happens? In practice, if I have n number of pins to connect, my interconnection topology will be a tree. There is no point in having a ring or a cycle in my interconnection, because I have to connect them anyway. That will be a tree typically. A tree connecting n nodes will be having n minus 1 edges. But in this case, when you have a complete graph, instead of n minus 1 edges, I am having n into n minus 1 by 2 edges, which is, well, which is you can say n by 2 times more than that corresponding to a tree. So, what we do here in terms of the estimate is that we find out the sum total of the edge length of the complete graph, all n into n minus 1 by 2 edges, then multiply it by 2 by n. Because in the complete graph we have n into n minus by 2 edges, but what we really want is n minus 1 edges. So, if I multiply this estimate by 2 by n, we will get something close to that. That is how we do it. We find out the sum total of all the edges, multiply it by 2 by n. That will give me the estimate of the average wire length for this net. Okay. Fine. But as you can see that here computation complexity is quite large. You will have to compute the cost for all n choose 2 edges and then do this thing. So means it is an expensive way of estimating. The second alternative is to have a minimum spanning tree. So, if you have several points, you try to connect them in a minimum spanning tree and try to find out the cost. The cost which you get, that is the actual cost, because the spanning tree or the tree is a structure which is close to reality. Okay. So that you do not have to multiply it with any weighting factor finally. Yes.
So, when you said you will find the sum of edge lengths,
yes,
for one particular edge we will find the distance, like straight line distance.
We will take an example. These distances are all computed as Manhattan distances, not straight line distances. Minimum spanning tree is a commonly used structure. Here branching is allowed only at pin location, just like a tree. When you construct a tree, well, edges can only come out from the vertices. You cannot take an edge out from the middle of an edge. This is the characteristic of a spanning tree. So, there are many algorithms for finding minimum spanning tree. You can just use any one of them. So, you will get this is also easy to compute.
So, but this is very obvious that branching is allowed only at pin locations, because the pin locations are actually the nodes.
This I am mentioning because you may have a situation like this, for instance, where you want to connect say a pin here, a pin here and a pin here. Now, in this case the optimal interconnection path will be like this. In terms of a graph, this edge is branching out from the middle. This is not a vertex. That is why I explicitly mentioned that point. Okay. Now, a graph topology like this, where an edge can come out from the middle, this is called a Steiner tree. In fact, the third alternative I mentioned is that a Steiner tree, rectangular means the edges are all horizontal and vertical, rectangular Steiner tree. Now, a Steiner tree is the closest to reality. Well, it is a tree all right, but Steiner tree is what we really do while interconnecting, because if it were not a Steiner tree, then in this example my interconnection would have been something like this. Say I connect this like this, I again connect this like this. Okay. So, in this case a wire can branch from any point along its length, but the difficulty here is that the problem of finding the minimal Steiner tree, this has been proved to be NP complete. So, although this is extremely desirable, finding the best Steiner tree is not computationally feasible, right. Okay. So, the measure which most people use today is something called semi-perimeter. Semi-perimeter concept is very simple. You have a number of points to interconnect. You imagine the smallest bounding rectangle which encloses all those points, smallest bounding rectangle, and you find the semi-perimeter of that rectangle. Find the perimeter, divide by 2. That semi-perimeter is taken as the estimate of the wire length. Now, the advantage of this method is that, well, this gives a good estimate. Well, in case of non-congested areas, this will give you the exact estimate. In case of congested areas where there are some obstacles in between, maybe you cannot draw the line straight, you will have to go through around, then it always underestimates the wire length. Underestimates means it gives an estimate which is less than the actual. This is unlike some other estimate where sometimes it can give an overestimate, sometimes it can give an underestimate, but this always estimates in one direction, so that your decision will never be wrong, right. Such when you are comparing two solutions, if both of them are estimating in the same direction, it will be easier for you to compare, otherwise your decision may become wrong at any stage, fine. Okay. So, these are the four ways in which people have talked about modeling the interconnection topologies. Let us take an example and try to see that how this estimate can be made. So, this example shows the problem of connecting these 4 pins. Okay. First, we talk about the complete graph. So, there is an edge connecting every pair of nodes. You try to find out the Manhattan distance of each of the edges. For example, this 1, 2, 3, 4, 5, 6 and 1, 7. So, the weight of this edge is 7. This one 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9. 1, 2, 3, 4, 5 and 1, 6. 1, 2, 3. This is 3. 1, 2, 3, 4, 5. This is 5. And 1, 2, 3, 4, 5, 6. This is 6. So, if you take the sum total of the edges, it becomes 15, 20, 30 and 36. 36. This you will have to multiply by 2 by n. Here n is 4, 2 by n is half. So, 36 by 2. Your estimate of wire length in this case is 18. Okay. Because the minimum spanning tree in this case, this will be the minimum spanning tree. Now, again estimate the length of the edges 1, 2 and 3, all are Manhattan distances 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 and 14. This will give the best solution, this Steiner tree 1, 2, 3, this segment gives 3, this segment is 2, this segment is 3, 1, 2, 3, this segment is 4. So, 7, 10 and 2, 12, this gives a cost of 12. In the semi-perimeter method, you just imagine the bounding rectangle and take the semi-perimeter 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 6 and 5, 11. So, as you can see, for complete graph you need a lot of computation. For minimum spanning tree you need to construct the spanning tree. Steiner tree is same, but semi-perimeter is very fast. Well, you basically need not compute anything, because defining this rectangle is very easy computationally. See the minimum x coordinate and the minimum y coordinate, maximum x, maximum y, you can find out from that. Okay. Fine. Now, in addition to these, there are some other issues which also need to be looked at when you are doing a placement, because there are a few issues which are very much dependent on the design style. For example, in a full custom, the blocks may be of various shapes and sizes, and since the block sizes are irregular, it may not always be possible to pack them in a very uniform and compact way. There may be some unused spaces in the corners. So, there may be unused areas. So, in a full custom design, when you talk about minimization of area, you are also talking about minimization of unused areas in addition to minimizing interconnection. Now, in a standard cell where all circuit elements are placed along rows like this, there first thing is that you will have to minimize the sum of the channel heights, because channels are the regions between the cells which are left aside for interconnection. Now, if your placement is good, you will be requiring less number of tracks in the channels for interconnection, your channel height will be less. So, a good placement will be minimizing the sum of the channel heights. Moreover, so a placement where some row is small in terms of width, some row is wider, that is not a very good way of filling up the rows. Well, in the ideal case, all rows should be of equal width. Minimize width of the widest row, that is one objective. So, all rows should have equal width, this is a desirable objective. Well, now in standard cell, there is a new concept which has come up. Normally, in the conventional standard cell, the space between the rows was kept aside for routing, but in a technique called over the cell routing, what happens is that, well, you have the rows of cells, the space which is above that, just above that cell, there are some layers of metal above that. So, those layers are used for interconnection rather than the space between two rows. This is called over the cell routing. So, if you can utilize this space right above the cells for routing purposes, then the channel size may become minimal. So, actually you can get some designs which are almost channelless. The cells are very close together and compact, the cell rows. Okay, so, these we will see later, what is over the cell routing. Gate arrays, partitioning and placement are almost the same, because when you are partitioning a circuit, your objective is to partition and place them on the surface of the silicon in terms of the gates. So, for gate arrays, partitioning and placement problems are the same, there is no difference. But for FPGAs, since the basic blocks on the chip, they are more complex than a gate. So, the partition sub-circuit, it can be a complex netlist. That complex netlist can map into one or more basic blocks. So, the problem for gate arrays and FPGA is slightly different, slightly simpler, I mean. Okay. So, now let us come to the actual algorithms which people use. Well, broadly speaking, the placement algorithms can be categorized as simulation based. Well, again simulated annealing and simulated evaluation are the better candidates here. There is a third method called force directed. There is a method which is based on partition. Partitioning and placement are going on together. There is a Brewer's algorithm and terminal propagation algorithm, and some other techniques. Cluster growth, this force directed can also be treated from a slightly different angle, we will be looking at this. So, we start by talking about the simulation based algorithm, simulated annealing. In fact, well, in the placement problem, the simulated annealing approach to solving the problem has been most widely accepted, because it gives very excellent result. In fact, very large designs have also been solved using simulated annealing for placement. Well, what is simulated annealing we have already seen. So, I need not spend much time on explaining what simulated annealing is. If you recall, you start with a solution, you define some moves through which you can modify the solution. There is a way of estimating the cost function. You make a move, evaluate the cost and see that if it is going to a better solution or a worse solution. If it is better, you always accept. If it is worse, you accept it with a certain probability. Now, in the initial stages of the algorithm, that probability is high. Now, as you go ahead, that probability goes low and low. Now, the algorithm, this simulated annealing applied to placement, this is called Timber-Wolf. This is the name of the algorithm which is given. Okay. So, first let us look at broad structure of the algorithm. Well, in this algorithm I am using the nomenclature which was used in the Timber-Wolf documentation. They called this temperature. In terms of reality, it is just a variable with a value. This is just a value, but they call it temperature. Capital T is the initial temperature and P is an initial placement. This can be done randomly or using some heuristic, you can choose this. There is another temperature called the final temperature. So, until you reach the final temperature, you repeat the inner loop. This is the inner loop. Now, in the inner loop, you iterate a certain number of times every time, while number of trials at each temperature not yet completed. This is defined as a fixed number, that at each temperature you iterate the inner loop certain n number of times. So, again you call a function perturb to modify the solution P to get a new solution new P. You determine the incremental cost increase delta C. If the cost is negative, then there is a better solution, you take this as a new solution. Else you again based on that random number, if based on that probability you accept it or else you do not accept it, and at the end of which, well, this is the inner loop, right. So, this inner loop is executed certain number of times. So, after that you modify the temperature using a function called schedule. You apply this function on the temperature, you get the new temperature. This is actually you are decreasing the temperature. This way you repeat this till the final temperature is reached. Now, in terms of this algorithm, let us look at the individual function, this perturb, this cost, this schedule, because the goodness or the badness of this method will depend on these functions or these measures of cost, for example. Yes.
So the temperature cannot decrease until and unless you have found a better solution. Only finding a better solution ensures that the temperature is conserved.
See, your question is that the temperature cannot decrease until we find out a better solution. See, the way simulated annealing algorithm works is that, say, at any particular temperature means the outer loop, you are making certain number of n trial moves. The inner loop is moving n times. Now, in this trial moves, it is always possible that none of these trial moves are accepted. Okay. So, in that case, in that particular temperature, you really do not get any better solution. You again change the temperature and repeat. But in general, what will happen? Some of these moves will be accepted, some will be not accepted. Now, the accepted does not always mean that you are getting a better solution. Maybe you are also getting a worse solution that you are accepting. But you will always be memorizing the current best solution you have seen, because that will be the final output of your program. Because what you get finally as P, that may not be the best solution you have seen so far. Maybe in some earlier iteration you had seen a better solution. Since this is a randomized algorithm and is not deterministic, you cannot say that finally you will always get a better solution. So, it must always also keep track of the best solution you have seen so far. Okay. So, this Timberwolf package, some details about that. Well, of course, this was developed by Sachin and Sanjivani Vincentelli. This was as part of a PhD thesis of Sachin. Okay, here the initial temperature was defined as a number 4 million. The final temperature was 0.1. And this schedule function using which the temperature was brought down, this was not defined as a linear function. This was some function alpha t multiplied by the temperature. Well, alpha t is a number, which is less than 1, but the way it was selected is like this. Alpha t was taken to be 0.8 when the cooling process just starts. This alpha t was 0.95 in the medium range. Again towards the end it was brought back to 0.8. So, the way you are doing the cooling, there also you are making some adjustment. In terms of a plot, it looks something like this. Well, I have this. This is the iteration number, this is the temperature on a logarithmic scale. So, this initial slope and the final slope are the same, in the middle the slope becomes different. So, through extensive experimentation it was found that if you follow this slope, the results obtained are better. So, there is no technical justification why this is chosen. This cooling curve has been selected through extensive experimentation. It has been found that this cooling curve gives it.
Exploring more values in the medium range.
Yes, yes. You are exploring more values in the medium range. Because initially maybe you are choosing, you are starting with a very junk solution, you are making some changes going towards a better one. After that you are exploring on that better one, and again towards the end we have already got some good solution, you are a little less well interested to make changes then, and this is the intuitive justification. And then the perturbed solution, the way the solutions are modified. Well, there are 3 different moves which are defined. These moves are fairly simple to understand. The first is that you move a block to a new location, simple move. The interchange of location between two blocks you exchange their positions. And third, you change the orientation. Okay, orientation in general may mean rotation or mirror imaging, but in this case they used only mirror imaging with respect to the x coordinate, just mirror image of the block with respect to x. But the way this move 3 was applied is that if this A was rejected, then only we apply C. Suppose you select a move A and you find out that by the probability criteria this was getting rejected, then you just try and apply C. So, C was not an independent choice, you first apply A or B. If A gets rejected, then you may apply C, right. Okay, now one thing to note out here is that, well, when you are talking about displacement of a block to a new location or interchange of two blocks, see, a feasible placement or a valid placement will be one where obviously no two blocks will overlap. But in this kind of algorithm, when you are saying that I am moving a block to a new block position, then I will have to check whether that movement will create an overlap with all other blocks. So, this simple checking itself will be of order n complexity, because there are n minus 1 other blocks. So, what this algorithm does is that it does not check this at every step. So, in the intermediate solutions there may be some overlap between two or more blocks. So, how this algorithm is tackling that situation? Well, this is allowing block overlap, but it will try to find a way out by defining the cost function in a suitable way. How? If there is a overlap, a negative, or means you can say some kind of a penalty is imposed, that is a part of the cost function. So, let us see how the cost function was defined here. So, the cost of the solution was computed as the sum of 3 factors, cost 1, cost 2 and cost 3. Cost 1 is the weighted sum of the estimated length of all nets. We have seen already how we can do this. So, you are finding out the estimated sum of the net lengths. Now, the thing to note is that you need not compute this afresh for the new solution, because you are making a move, just the portion which is affected by the move you can recompute that part. So, this can be an incremental computation, not necessarily you are computing the entire thing for the new solution from scratch. Cost 2 is the penalty cost for overlapping. So, if there is an overlap, you incur a cost.
But how do I find this cost too? I have to actually find out whether overlapping has taken place.
Yes, yes. Here for computing the cost, you have to check that. Yes.
So
But while making the moves, you do not check that.
But with every move I am calculating its cost.
In a sense, you can say you are in a sense you can say that for every move you have to calculate the cost. You are checking this anyway. But if you are say means the idea that if you are excluding block overlap at the intermediate stages, then possibly you are excluding some of the better solutions, because maybe some blocks will overlap, but since the cost will be increasing, some of the other block will move out to some other place, maybe in some later generation. That is the possibility we are keeping open. That is not exactly what I had mentioned earlier, that you are not computing cost every attachment. Yes, we are computing the cost, but we are also opening the possibility that there can be an overlap, but the other block may be moving out, possibly leading to a better solution, because we are also including that in the cost penalty. And cost 3 is that, see, this method was initially or primarily applied for standard cell placement, because standard cell placement is the most commonly and widely used placement we use today. Cost 3 is a penalty cost which is used only for standard cell kind of a placement for uneven length among standard cell rows, like one of the row may be narrow, one row may be longer, one row may be this size. So, there is a cost depending on the unevenness of the rows. So, they defined an expression for this also. These are the 3 components, it is the sum total of these 3. So, here as I had mentioned, overlap is not allowed in placement, but it is computationally complex to remove all overlaps. So, we allow overlaps to occur, but we incorporate this in the cost function, so that most likely with respect to the cost we will be moving towards a better solution which will remove that overlap. Okay. So, today in this lecture we had talked about one very popular algorithm or method which is used in placement. Now, in our next lecture we will be looking at several other techniques which are used for placement, simulated evaluation, force directed scheduling and some other partitioning based and cluster growth kind of a technique. You will see that some of those methods are good as standalone ones, some of them can be used to generate the initial solution for the simulated annealing kind of algorithms. Okay. So, this we will be seeing in the next class.